Today, we'll be talking about depth perception. So what is depth perception? It's seeing objects in 3D, right? So this is what allows us to judge distance. If you remember from last unit, we talked about how as you get older, you start to lose your depth perception, and that's why, elderly people tend to fall a little bit more, one of the reasons. And that's because they don't judge distance as well because their depth perception has declined. So we're going to focus on two types of cues, right? So we'll talk first about monocular cues, mono meaning one. So all of these only depend on one eye. So you could do all these things with only one eye. Relative size, relative height, relative clarity, relative motion, which is also called motion parallax, interposition, texture gradient, and linear perspective. That's why when we do a photography project, you have to take pictures of things. We're only doing things with monocular cues because that's what a camera is. Now the binocular cues, you need two eyes to do this. That's why you can't do those with the camera. You can't do any of those with on the camera project. So the binocular cues where you need two eyes for, this is called retinal disparity, convergence, and divergence. So first, let's talk about monocular cues. And as you can notice, it's not necessarily a lot to write down, but it's a lot to remember. So you really have to take notice of the pictures and why I'm showing the different pictures, and then use what we're talking about for that. So relative size is using the perceived size of a familiar object to determine depth. The larger the object appears, the closer the object is to the viewer. The smaller the object appears, the farther away it is to the viewer. So a lot of what we're going to be talking about in this set of notes is very common sense, especially if you're an artist. If you've done any kind of art before, we're just going to be using those same principles now, and I'm just going to give you examples of different pictures. So relative size, right? So if you look at the graveyard here, you have a bunch of Celtic crosses. We know they're relatively the same size. But this one, if you measure this one, takes up almost the whole screen. And this one here, takes up like a third. Right? So because this one is larger, we know it is closer. Because this one is smaller, we know it is farther away. That is all relative size says, right? The closer the object, the larger it appears. So if you look at this, you have a row of men. They're all about the same height, but yet the ones close up, right, they take up the full screen, and the ones far away take up a third. They're probably within an inch of each other, but yet, this one looks a lot smaller because he's farther away. He looks a lot bigger because he's closer. That's all relative size is saying. Relative height is the method of determining depth by knowing that distant objects appear higher in your field of vision than do closer objects. This is actually reversed above the horizon where higher objects seem closer. You know that the trees and the houses, right? So the trees and houses right here are farther away than the lake. So here's the lake because they're higher up in the drawing. Right, so anything that's higher in the drawing is going to be farther away, unless it's above the horizon, and I'll show you an example of that in the next picture. And you can pick out anything from the picture, as an example. If it's higher up and it's below the horizon, it has to be farther away. That's just the principles that we're working with. Once again, if you're an artist, these are things you already naturally do. So here's an example, right? The cactus on the right is farther away than the cactus on the left because it's higher up. Where the birds is actually the opposite. So the bird on the left is higher up, but it's actually closer to us. All right, so once you get above the horizon, it actually reverses. All right, so the higher it is in the picture, the farther away it is. Unless it's above the horizon like the birds, then it's closer to you. Relative clarity. Method of determining depth by knowing that distant objects are less clear than nearby objects. Right? So if you look at this picture, the distant mountains look blue and hazy because of dust and moisture in the atmosphere. Makes it look a little not as clear. So like I said, a lot of this is just common sense. Right? So obviously closer things are going to be clearer. So if you've ever drawn a picture and you're drawing something in the background, a lot of times you don't draw great detail. You just kind of shade things in and make it a little fuzzy. That kind of shows that it's farther away. So if you look at this picture up close, you can see the details of even the beams, where when it gets farther away, it becomes a little blurry. That's relative clarity. This is also linear perspective. So remember that. We're going to talk about that soon, right? So parallel lines start to converge. Relative motion. So in this example, the passenger is moving past a stable world. If she fixes her gaze on the bridge, objects behind it will appear to move forward. The farther away the object is, the more slowly it appears to move. Objects in front of the fixation point appear to move backwards. So if you've ever been on a train or a car and you look out right by you, it looks like everything's flying by you. But if you look in the distance, depending on where it is on your fixed point, if it's closer than the horizon, it's going to move along slowly with you. But if it's farther away than whatever you're fixed on, it's actually going to look like it's moving with you. So once again, everything close to you is going to move quickly behind you. All right. So the farther the object away, the more slowly it's going to appear. So things back here are actually going to move with you, but slowly. Anything that you're fixed on will move backwards though. And so this is one you could do with your picture project. And what you do is actually take like a short video, like a 5-second video, something like that, even shorter. And you're gonna fix it, but it has to be somewhere where you can actually see in the distance. So you can see things in the distance look like they move with you, and everything close to you, you'll see it fly by. Now, of course, I have to put the disclaimer out there. You cannot take a video while driving a vehicle, right? You have to be the passenger or have the passenger do it, or do it in a train, something like that. You cannot be, conducting the vehicle while taking a video. So even though this is a still frame here, you can still see what's going on. So even though this is a still frame picture, you can still see how up close, right, the railing, this part's a little blurry because it's moving by fast, where the things in the distant, like the mountains, are clearer because it's going to look like it's moving with you, right? So once again, that's relative motion or motion parallax, same thing. Stroboscopic motion. This is the illusion of motion by rapid projection of slightly changing images. All right, so it's a concept in motion pictures like what movies use, or at least I know that's what they used to use. I'm not sure with digital anymore. But think about like a cartoon, right? I'm sure you guys have drawn it before, where you kind of draw different figures, kind of like you see here with the stick figures. And if you flip like a book, it looks like it gives motion. That's all this is, right? So something like this. You can do this on so this could be one of the things you do for your picture project. I've had people do like the actual flip book with like the little mini pads, or now with technology, a lot of times they'll do this. I've had people do this on their iPads. I know Snapchat had a feature, I think it still does, where you can do stuff like this. Induced motion. So I'll show some examples when we meet in person and post some videos, but induced motion is just where Carl Dunker studied this with the dot and the moving rectangle. The rectangle moved, but people thought it was the dot moving. This is because of top-down processing. Remember, we talked about that earlier. It's where people expected the dot to move and our assumption that the background is stationary. So induced motion, in fact, I don't think there's a good video for it. I've tried finding some. If I do find some, I'll show you guys. But so you have the dot, in the middle of the picture, and the background is actually moving, but our eyes make it look like the dot's moving, and that's because top-down processing, because we assume that the background is going to be stationary, right? That's just the assumptions that we make. And so it looks like the dot's moving, but in reality, it's actually not. It's actually the background moving. That's called induced motion. Interposition. Right? Method of determining depth by knowing that closer objects partially obstruct, block the more distant objects. This is also called overlap. So this is simple, right? If something's blocking something, it must be in front of it, right? So the king of clubs is blocking the king of spades, therefore the king of clubs must be closer, right? Because it's blocking it. Right here, right? So who's in front? Bambi A or Bambi B? Hopefully you said Bambi A, right? Because it's blocking Bambi B, so we know Bambi A must be in front. Texture gradient. This is method of determining depth by knowing that distant objects have a smoother texture than nearby objects. All right, so if you look at this picture, individual flowers are visible in the foreground, but in the distance, they kind of smooth out like a smooth carpet. Right, that's texture gradient. Where up close, you can see the details of everything, and as it gets farther away, you don't, it just kind of smooths out. So here's another example of like a brick sidewalk. Up close, you can see the texture of everything. As it gets farther away, it becomes kind of smooth. You can't tell. I've had some good pictures in the past of maybe taking the picture of like the side of the brick building, where up close you see the bumps of it, and it kind of gets smooth farther away. Also, like grass, so up close you see the different blades of grass, and it kind of smooths out the farther you get. Um, you know, you can use the examples I give you, but obviously, try to be creative if you can. I know some of you guys are very creative. All right, linear perspective, right? This is the method of determining depth by knowing that parallel lines appear to converge in the distance, right? The lines appear to eventually merge on the horizon. So the sides of the road seem to converge in the distance, right? So we know it's parallel and they converge, just like the picture I showed you earlier. All right, so parallel lines, the farther away it gets, it's going to converge, just like the railroad tracks I showed in the other set of notes. The subway station I showed, any parallel lines, the farther away it gets, they start to converge. So, lots of things you can do for this. You could take a picture of a sidewalk. I have people take pictures of roads. Of course, I always have to do the disclaimer, make sure there's no cars coming, make sure you're looking out for that. The hallways, if they're clear. So anywhere you see parallel lines, you could do something like this. You also see it in pictures, right? So this is a famous picture. I think Raphael did it. I don't remember. Pretty sure it was in the world history book when I taught world history. I kind of remember this picture. But you see linear perspective here because the artist is actually using parallel lines to match up, right? The columns, right? So you see the different arches as they go on. They're actually using parallel lines for this. And I remember seeing something on like Leonardo da Vinci, he did the Last Supper, and they're talking about just the math and how those Renaissance artists used linear perspective and how their math was exact to show depth and to show distance. So that's exactly what they're doing here. Light and shadow, right? So this just says nearby objects reflect more light into our eyes. So given two identical objects, the dimmer one is going to seem farther away than us, right? Because the brain always assumes that light comes from above. So you can kind of see in this picture, right? As it flips, it looks like so it's the same picture. It's just one's, upside down versus the other one. And depending on where the light is, whether it's closer to you or farther away from you, it looks like there's like a hole in the ground or like it's concave, like there's a bump there, right? And that's all because of the way the light's hitting and your brain's making assumptions. And then on the right, you can just see the different shadowing and, same similar circle, but just depending on how you shade like a circle or an oval gives it depth, whether it makes it look concave, like there's a bump or like there's a hole there. So now we're going to talk about some binocular cues. Remember, for binocular cues, you need both eyes, right? So these are ones you can't do for the picture project with the camera. So retinal disparity is one, right? So it compares the images from the retinas and the two eyes. The greater the difference between the two images, the closer the object. So for this one, you could do one where if you hold your fingers parallel, and if you guys can't figure this out, I'll help you when we do our video chat. You have your index about 6 inches apart, and you move them so one closer to you and one farther away from you. They're still going to be 6 inches apart, but as they move farther away, they look like they converge on each other, right? That's retinal disparity. Here's another example of retinal disparity. This is called the finger sausage. All right, so it's kind of cool. So if you hold your fingers out, right, about 2 inches apart from you, and you have to stare through your fingers, right? Don't stare at it. Both eyes have to converge through, so they'll kind of like stare at a point beyond you, and it's going to look like there's this little mini like finger sausage like kind of floating there. And so what you can do, you can slowly move your fingers farther or closer away from you to see that finger sausage, but always keep those index fingers a couple inches apart. And once again, if you're struggling with this, I can kind of show you as best as I can on a video chat. All right, so an audiocerogram. So this is just another way to create the illusion of depth through retinal disparity is with an audiocerogram. So what is it? All right, so make sure you know this, right? An audiocerogram is formed by superimposing two repeating patterns. All right, so the two separate patterns are slightly offset, and when viewed properly, this offset is seen as a binocular disparity. So this is like if you've ever seen a 3D movie and you take your glasses off, notice how it looks like two superimposed pictures right on top of each other? That's all this is right here. And so on the next slide, it's going to look like a kind of just like a fuzzy like picture. Or actually, it's going to be in two slides. The next slide is going to be directions. So you don't need to write this down, but just if you want to, see the 3D image on the next slide, this is what you do, right? So to see the 3D image, you're going to first view the picture closely. So it should be easy on your computer or whatever you're using. Focus your eyes as if you're looking at some far off distant object. Look through the object. Try relaxing your eyes so they swing outward. Without changing your focus, slowly move away from the picture. The image will begin to come into focus. Do you see a face? If you have trouble, it just means that your eyes are difficult to trick. They want to focus at the proper depth. So let's see how well you guys can do. So just stare at the picture. Stare at the picture. Relax your eyes. Let them swing outward. Act like you're looking through the picture. Looking through the picture. Just relax them. Might take up to 30 seconds. Relax. Stare through the picture. And eventually, you might start to see a face. Now this, I think, is one of the harder ones to actually see. The other ones people can usually get. There's only usually a few people that can actually see this one. I usually struggle with this one as well. All right, so convergence versus divergence, right? So the two eyeballs focus on the same object, and doing so they converge, right? That's where things come together. I always think about plate tectonics. I'm sure you guys have learned about that before, like the plates that the Earth is on. We have three types of earthquakes. We got transform where they slide by each other. That's like California. That's why you got the San Andreas Fault in California, which you can actually see from space, where eventually, the southern part of California, southwest part of California will break off. It might be a couple thousand years, but eventually they'll slide by each other. And then you have convergence. That's where two plate tectonics, they collide with each other. They converge. That's like the guy on the left, the kid here, the cross eyes, that's where your eyes converge, so you're staring at something in the middle. And then you have divergence where they come apart. So just like you also have earthquakes where the plates are coming apart from each other. And so you see this in the middle of the Atlantic Ocean. There's actually a mountain range coming out of the Atlantic Ocean because the plates are splitting apart, and then the lava comes up and then hardens and it builds. And that's actually how you get some islands are built that way as well. Well, something different. You have hot spots. That's how you get the Aleutian Islands and the Hawaiian Islands and stuff like that. But so the Atlantic Ocean is actually getting bigger every year by like a centimeter, and the Pacific Ocean is actually getting smaller because it's converging with the Pacific plates going into the Asian plate. Perceptual constancy. So we're going to talk about a couple different things that are constant, and all this means is where they might look different, but they're still the same. The phi phenomenon, I'm gonna have to show this to you guys when we do a video chat. I can post a video. I think there's some videos as well. There's a good website with this. And what you do, so the illusion of motion is motion when fixed lights are turned on and off in a sequence. So to see how this works, we're gonna look at this website. So what you're gonna do, you're gonna stare at like there's like a cross or a plus sign in the middle, and you're gonna see like green dots going around a circle. Well, if you eventually stare at it, it's going to look like it's a red dot going in a circle, and eventually all the green dots will disappear, and you only see this like pink dot going around. Now, do they actually disappear? No. But when we talk about vision, you're going to see that our vision has these pairs, and you're going to kind of exhaust, right, one color, and then you're going to see the other color. All right, so now we're going to start talking about the constancies. So size constancy. This is a person's understanding that as an object moves farther or closer to them, its actual size stays the same. So as an object appears to become larger, we realize it's getting closer, not bigger. As an object appears to become smaller, we realize it's moving farther away, not getting smaller. So this is similar to like relative size, in relative height, things like that. But to do the picture project for this, you're actually going to have to show two pictures of the same thing, one close to you and one farther away, and to show that it's actually the same size, it just looks different based off the picture. So if you see someone down the hallway, they look tiny, and they get close to you, they could be huge, they could be 7 feet tall, right? Now, do they grow as they walk down the hallway? No, they're just closer to you, so they look bigger, but we know that they're actually the same size. Right, so once again, for all the constancy pictures for the picture project, you'll have to do two pictures of the same thing, one close, one far away, and just explain how they're actually the same size even though they look different sizes in the picture. So we see this here, right? People are the same size even though their image sizes differ. So the depth cues such as linear perspective and relative size help the visual system judge the size accuracy. So here we have linear perspective. We see the columns getting smaller as they get farther away, but the person looks like they're giant, right? They look like a normal person. As they go farther down, this person looks like a giant. If you actually measured him, they're all the same size. But because of our our cues that we've learned, as he's getting farther away, because linear perspective says he should be getting farther away, he's higher up, all those things, he should be getting smaller. So obviously that could not be a real picture if it was the same person, or you're dealing with giants. So shape constancy. All right, this is the understanding that an object's shape remains the same even though the angle of view makes the shape appear changed. So here we have an example of three doors. Right, so we know the door is always the same, but depending on the angle, it's actually a different shape, right? So the one on the left is a perfect rectangle, the next one's opened a little bit, and the next one's open a little bit more. If you were to trace the shape of the door, it's actually a different shape, but yet we know it's still a rectangle, right? That's shape constancy. So once again, you'll have to take at least two pictures of the same object from two different angles. So obviously, you could do a door, people do books, all kinds of different things you can do, just to show that it might look different, right? It's a different shape, but yet we know it's still the same shape. It hasn't necessarily changed. Here's another example of shape constancy. So it's hard to tell if the figure on the upper right is a trapezoid or a square slanted backwards because it has no texture to it, right? So it could be either one. So, but if we add texture to it, the texture gradient helps us see that it's actually a square. So because the dots get smaller and they start to converge on the right, on this one right here, we know it's just a square that's leaned backwards. If it was a trapezoid, then all the dots would be the same size and the same distance from each other. Light constancy, all right, the ability to see an object as having a constant level of brightness no matter how the lighting conditions change. So if you look at a sheet of paper in bright sunlight, it looks blazingly white. View the same sheet in a dimly lit room and it appears gray. Has the paper changed? Of course not, right? We know paper stays white no matter what the lighting conditions are. So light constancy, or sometimes are also called color constancy, we know that it stays the same, right? It might look different because you're in a different lighting, and that happens all the time. So once again, you just have to take two pictures of the same thing and two different lightings and just show how it looks different, but yet we know it's still the same light or same color. Depth illusions, the last thing we'll talk about. So sometimes our perception of depth can be tricked. So there's a lot of different examples of this. I'll post a video of this, and we can maybe talk about this when we meet online as well. One is the face mask illusion. So you're going to see a mask rotating, right? But then when it flips, and you're looking at the inside of the mask, it's actually going to look like it starts rotating the other way. It doesn't, but that's just your brain playing tricks on you because you assume what the face is going to look like. So you see the shadows of it, and your brain always is going to try to make sense of it and make it look like a real face. So it does that, but then it goes in the reverse direction. You'll see on the video and when we talk. And then the last one is Julian Beaver. He's this crazy artist. He does this sidewalk chalk, and he has a bunch of websites. I'll show you some websites when we meet some of his work. So if you look at the one on the left, it looks like he's standing on the world, right? But if you look at the right, that's what it really looks like. It's all about depth perception. So he uses all these cues that we've talked about to make these 3D images. And here's another one that he does, right? So on the left, it looks like he's literally putting a foot into a swimming pool, right? That's all that stuff that he's drawn. And I'll show you his websites. You can go check them out if you want. They're down there as well. But so he uses all these cues we talked about and makes it look, but it's only from the right angle, right? So it has to be from the right angle that you see it looks like a 3D pool, like he's getting a pool. Now, if you look at it from the other direction, like the picture on the right, you notice that her leg is actually extremely long, right, from the other view. But from the right perspective, it looks like she's just sticking her leg out of the water. And like I said, he has a website with tons of of these images that he's done all over the world. And there's a couple other artists that I'll show you as well. That's pretty crazy what they can do just knowing how to use these different like monocular cues.